Pues bienvenidos todos. Esta es nuestra última conferencia del ciclo de conferencias diálogos entre matemáticas y cultura. Tenemos el agrado de presentar a Michele Emmer de Italia, en donde nos hablará sobre las pompas de jabón, arquitectura, matemáticas. Y por último quisiera decir un poco sobre su semblanza. Él ha trabajado en superficies mínimas y cálculo de variaciones y entre la relación entre matemáticas y culturas. Ha realizado 18 películas en la serie de arte y matemáticas, incluyendo la película sobre Escher. También tiene una exposición de pompas de jabón en la Galería Nacional de Umbria en 2019. Ha organizado diversas conferencias de matemáticas y culturas que dieron origen a una colección de libros en Springen Verlag que se llama precisamente Mathematics and Culture, y tiene muchísimos más trabajos de publicaciones en periódicos y en revistas y en diferentes tipos de libros. O sea, tiene un trabajo muy extenso sobre la difusión y divulgación de las matemáticas y es un honor para nosotros tenerlo presente. Welcome, Michelle.
Muchas gracias. Buenos días a todos. Unfortunately, I cannot speak a very fluent Spanish, so I will speak in English. It's a pity because my wife is Colombian, but in 20 years I was not able to speak very well in Spanish because it's too similar to Italian. So you have the impression to speak Spanish, but you are speaking Italian. So I will talk about the pompas de jabón en arte, la matemáticas y la arquitectura. Voy a comenzar con, esta es una postcard del 20th century that my grandmother received in 1904 from Germany. It's the address of my grandmother. Of course, it's a game for children. It is impossible not to look at the bubbles blowing in the wind. There are very serious people who make also bubbles. It's possible to make also very, very, very large. There is a sort of world competition to make the longest bubble. But not really this kind of bubble that are interested in mathematicians. Georges Bizet made the music. The title was Boule de Savon in 1871, and the year is very important. You will realize at a certain moment. I translate this in, Marcela translates for me in this sentence by Lord Kelvin. Haz una pompa de ron y mírala con atención. Podrías pasar toda tu vida para estudiarlo. And Lord Kelvin posed a question, a very famous question that was physically solved only a few years ago regarding these minimal surfaces on which the subbubbles are examples. Not really totally correct, but more or less. And this is another sentence by Mark Twain. So bubbles is everything most beautiful in nature. I wonder how much it will cost if there is only one bubble in the world. And you will have an idea of the cost of a single bubble later on. Mark Twain, The Innocent Abroad. I will talk with art, and I became interested in some bubbles because I was involved after my degree in Rome in 1970 with minimal surfaces. And then I went to Princeton, and very close to Princeton there was the math department. And so, just for joke, I went there, see if there was some picture of bubbles to illustrate a paper I was writing on minimal surfaces. And I discovered really a world of hundreds and hundreds of engravings, paintings related with the theme of soap bubbles. Of course, in the 80s, it was quite complicated to make research on images because there was no internet. So everything was made by fax. It was really, really complex. But in any case, this was one of the first, this engraving is Boucher, 1758. But this was very, very serious subject for research. Not only mathematics, but physics and chemistry and many other fields. This is the paper by Gilles de Gennes when he received the Nobel Prize for Physics, 1992, for his work on soft matter. And you cannot read probably, but there is a part of his work was dedicated to soap bubbles. This is one of his books, Les Objets Fragiles, and also in his book there were 2 or 3 pictures about soap bubbles. So I asked him to send me a picture of a Japanese painter. It's a little bit difficult to see exactly where the 2 bubbles are because it's a little bit on the right of the head of the lady. There is a story why in the 19th century some Japanese artists made bubbles, but I will not enter into the details. And the story, I start also with some element with the scientific story of the soap bubbles, the soap film. And this is a famous book by Boyce called Soap Bubbles, will be translated everywhere. And he has the idea, it was not really his idea, but he used the idea of Plateau to make a sort of public presentation of a scientific show of soap film and soap bubbles. And invented how to do it, because of course there was no computer, no slides, nothing of this kind. This was really beautiful. Usually it was something was made near Christmas. And this book was published in 1890. It was very successful everywhere. But there's also there is a continuous interest in minimal surfaces. We will see at the end of the first part that several mathematicians received a field medal working on minimal surfaces. And this is a paper on minimal surfaces published in AMS, American Mathematical Society Notices, in April 2017, a new golden age of minimal surfaces. Yeah, this new golden age, but it never ended. It's always a golden age for minimal surfaces, I must say. This is the cover with some example of minimal surfaces. I must say that when you talk about soap bubbles, to be precise, soap bubbles are not minimal surfaces, of course, because that is the curvature. So the correct way to talk about soap bubbles is surface, minimal surface with constant mean curvature. Otherwise, it's not correct. But you can say an example of minimal surface are soap film and soap bubbles. This is interesting because I don't know if you know one of the most famous architects in the world. She died almost 5 years ago. We made an homage to the conference in Venice. And one of his chief architects of his atelier in London came. And there is one of the series of mathematical sculpture, in particular, I think is Image Math G5. There is 35 pages on her. There is Zaha Hadid, who had a PhD in mathematics, and that she used several times, many times, minimal surfaces in her architecture. And I will show just, I will not read this. So, Science Museum of London, which is a very, very old institution, there is the room who Zaha Hadid made on new result on mathematics. There are several examples of minimal synthesis, but it's very, very modern. Inside this building, very, very, very old, 18th century, 19th century. So the connection with art. This is a frame of a film to 2003 called The Girl with the Golden Handles. It's a story of the famous painting by Vermeer, 17th century. And these are the four girls of Vermeer. And you see that they are all playing with soap bubbles. It wasn't, say, normal that the Dutch town, the 16th, 17th century, people, in particular children, were playing with soap bubbles, because the problem is that only perhaps the 15th century was created a soap that produced bubbles, because the soap that were used before was not producing bubbles. The soap of the Romans was made with oil or olive, does not produce bubbles, so it simply doesn't exist, a bubble. But the idea of the bubble and the connection with the theme of the Vanitas is very, very old. Greek, Rome, and Latin. But the bubble was the bubble of air in water, not the soap bubble. So when started this history of soap bubbles in art? This, if you look at is inside the great theme of the Vanitas. So you will find these engravings by Goltzius. It is the 1594. Quis evadet, who escaped to death, etc. But in reality, there are many, many examples before. So we are in the siglo XVI. This is interesting because it's the discovery that I made in the Cathedral of Mallorca, the Balearic. This is where it is written, but I will not read it. This on the floor of the cathedral in Palma de Mallorca. And you see that it's almost the same as the one on the right. The people there never realized that this was sub-bombers. They thought it was a boy with little balls, not sub-bombers. So it became very famous in engravings of gods. So I will show you some example of painting with so. There is written in Greek, Pomphulus or Anthropos. They mean the life of a person is like a bubble, soap bubble. And then you see the author and the date up on the left. And this is quite small. And on the other side, there is a portrait of the person who asked to make the work of art. We are in Germany. It's always before the engraving I show you at the beginning. Homo, there is written very clearly Homo bulla. Erasmo da Rotterdam invented the Homo bulla. The other on the right is on glass. This also was unknown by the author, but this is 18th century. And this is Dujardin. This is very important because, for me, of course, it's from Denmark, this painting. It was very, very beautiful because was the poster for the exhibition of 2019 in the Galleria Nazionale dell'Umbria in Perugia. They started in March, just a little 2 months before the COVID. We were very lucky. Other of the paintings, Van Mieri, we are in Holland. There are many, many paintings on the topic, and also the topic of the window, which is typical of the paintings in Holland, Van Mieri. And this is Casper's Nature. This is the National Gallery in London. This is one of the paintings in the exhibition in Italy 3 years ago. This is Flink. This painting was destroyed. And in the 16th and 17th century, there was they used to make the portrait of a young girl, a young boy, with an object that was very important for him or for her. And many of them had some bubbles. So, in a sense, there was in the painting, all this history of painting with some bubbles, there are sort of two different ways. One in which the prevalent interest in as a theme of the vanitas of human life, and the other, of course, toward the children. So they play with the so bubble. This is one of the masterpieces, David Bailey. You will see on the end right, Vanitas Vanitatum. It is a Fresnel portrait, so he is the painter. And you see the bubble. And then, of course, the problem with the bubbles, if you make a picture, painting of the bubble, they are transparent. So you have to give the impression of the three-dimensionality, and so they use light reflection to give this impression. There are all symbols of death, the skulls, etc. This is the tail of the painting. This is a really large painting, which is also always in Holland. This is Dosso Dossi, an Italian painter, but this painting is now at the Getty Museum in California. The Fortune, and there is the bubble over there on the right. And this is another painting of David Bailey. When I made my book about 20 years ago on some bubbles, it was not a tribute to David Bailey, but now there's the experts say that this is David Bailey. Oh, I remember that I told you how much will it cost to have to buy bubbles. There were only one in the world. Well, this is Rembrandt. It is a private collection of the Prince of Liechtenstein, who gave two of his personal paintings for the exhibition, but not this one. He said, "This I cannot move this from the gallery. The museum is reality is in Vienna." So this painting was bought by him for 8 million euros. So, what is the connection with science? So bubbles and science. This is a painting of the 19th century, and the person there is Newton, who is looking to a little boy who is making bubbles. I repeat that there are hundreds, thousands of paintings in France, in Germany, in England, in Belgium, almost everywhere, also in Italy. Less, but also in Italy. So it was very usual to see people, the young girl and boy playing with soap bubbles everywhere. And Newton was the first to notice that on the surface of the bubble, you see color. And he tried to explain why. So he's the first one to pose the question. Well, if you ask the same question to Hooke, who was the enemy of Newton, he will answer, I was the first, and Newton was the second. But the written words say that it's Newton. So this is Optic of Newton, London, 1705. There are about 10 pages related with experiment to make with, he has no explanation why there is the color, but he suggests several experiments to make with the bubbles to try to understand why they have always the same structure, etc., etc. And what is interesting that the boys, the person who I read you a few words just at the beginning, who published the book on soap bubbles, the first book on soap bubbles, was one of the first book who has a color plate inside. Color plate is one on the right. This is the original plate of the book. And on the left there is a big little experiment. So they have those two. You have two surfaces when you put inside the water with soap, little structure. And then when you put it out from the water, and you will see that the water will fall down, and when the length of the distance between the two surfaces is reducing, and then there is exactly the color that you see on the surface. It's exactly the same that happens when you make soap bubbles. So Boucher's is the same that we saw before, with another engraving. We are always in the 17th century. And this is Chardin. Chardin is a very, very famous French painter. And we were very lucky because this painting arrived to the exhibition, not the other one from the Metropolitan Museum. It's different from this. I will show this. There are three versions of this painting. Metropolitan Museum, one in Los Angeles and one in Paris. But this one is in Stockholm. Is in the Hermitage in Moscow. So is one of the paintings considered with no price. There is no price to buy a painting like this. And I will not tell you how complicated it is to receive a painting like this. It takes days and days, and only to open the enormous structure when a van comes to the museum, to open it takes 3 hours. But it was there. This is a small painting, while the other is big. And of course, these two paintings are in the interest of the painter for the boy who are playing with the soap bubbles. The three version of this painting is different only in some detail, little detail. What is also interesting is that a sort of evolution of how to make the bubbles. I will not say nothing about that, but and the other thing interesting is the little color that Chardin put the blue on the bubble so that you see the bubble. We have the 18th century. Of course, this is another with the girl and boys playing with soap bubbles. And then there is Napoleon. I just saw yesterday the film of Ridley Scott on Napoleon. I don't know, it was just... I presume that in the US it is already on the screen, I don't know, in Mexico. So this is Napoleon. That gives a lot of kingdom to his son. He will remain in sort of prison for all his life, of course. And this is very interesting because I received this from the Catholic Journal of the Vatican because there was not in my collection of my book. So they sent me this. It was this French Revolution that destroyed the bubble of the Pope because the law of the Pope are called in Italian bolle. The same word that bolle di sapone. So it's not the same in English, but so this is the reason why the French Republic is destroying the bubble of the Pope. We are now in the 19th century. This is Chaplin. This was the museum in Paris. But unfortunately, the museum during the Second World War was destroyed, so this painting does not exist anymore. While this one the sculpture is at the Metropolitan Museum. You notice that these, also with the boys and the girl, there is a sort of melancholy. There are the bubbles, and you are thinking of your life, something like that. So we are in 1887, and then another masterpiece, Manet, 1867. We know the name of this boy who is playing with the bubbles. And this is the Gulbenkian collection in Lisbon. It was not possible to have it because they don't move the painting. But it will give us the permission to reproduce the catalog. The painting. 1867. Now, the geometry of some bubbles and some film. This is a picture of a US artist, Bradley Miller, who went to Princeton to study not mathematics, but to understand something about the structure, and I will explain why in Princeton, of soft film. And he's specialized in making pictures in black and white and in color of soft film and soft bubbles. So these are all pictures by Fraiotto. This is from Fraiotto. I will talk later on Fraiotto. These are all pictures of Bradley Miller. When you wash dishes or you drink a beer, there is an enormous kind of surfaces connecting together. You can have the impression that there is a lot of angles that the surface creates. But if you look at this picture, you immediately recognize that here there are angles of 120. Well, the idea of Plateau, the person in the 19th century studied the problem, was that there are only two kinds of angles when you connect minimal surfaces. Or minimal surfaces means also fluid in the cell and in many other things. There are a lot of applications. Only two kinds. This kind, also the proprietà isoperimetrica, I don't want to abuse of the time. Perhaps I will not consider this. Let's go directly to the law of Platon. First of all, see the date. Exactly, is more or less the same date of the painting of Manet. A coincidence, by chance. And the two laws, I translated in Spanish, are this. All surfaces of soft film can create only two kinds of intersection, or three, the middle center of the tetrahedron, or six, that they produce an angle of 109 and 28. So, or 120 or 109 and 28. This was the conjecture of Plateau, who made this only experiment. He was a physicist, a chemist. But almost nobody or mathematician said that this seems so strange. It is the solution of the problem. So these are the two examples, 120 and the other 109 at the center. It was a conjecture, 1872. It was proved in 1976 at Princeton. This is the reason why Bradley Miller went to Princeton, by Gene Taylor, using the result of Fred Algren, who was also his husband. It is one of the most famous papers on minimal surfaces. And the result is that Plateau was right. There are only two kinds of structure that you can obtain. And that is, of course, the drawings that are in the book of Plateau. There are also something else in the book, and these are structures that are called radiolaria. They were studied, are still studied microscopic organism that part of the plankton. The reason is that the silicon of the structure made the same angles like the soap film and soap bubbles. The person who realized this was Darcy Thompson at the beginning of the century, the last century. On growth and form, there is about 60 pages on soap film and soap bubbles, a result of the plateau, an example in nature of structure, like the plankton, you can see the angles of plateau. And the interesting thing that the images of the radiolaria, after a tour around the world for 3 years of the Challenger, the ship called Challenger, they was reproduced by Ernest Haeckel as scientific work, and then they became ideas for Art Nouveau, the artist of the beginning of the 20th century, whose Fullman naturally. This is the paper of Fred Argan and Gene Taylor on Scientific American, the same year the publication of the scientific paper. And also in the paper there was a structure of the radiolaria. Almost all the people said, well, it's impossible that you see something like that, because there was no electron microscope, there was only an optical microscope. It's impossible to see the radiolaria like this. Well, this is called nacellaria. This is the drawing of Haeckel, but this is electron microscope. How Haeckel saw the structure is not clear because there was no electron microscope, but the drawing is exactly this. And the interesting thing is that this is a sculpture. Well, this is a structure with this real soap film. But now Gabo had the idea to use this picture, this object, to produce a series of sculpture based on a radiolaria based on soap film structure. Exactly this. This is always the page about Darcy Thompson. Darcy Thompson wrote this, la peculiar belleza de la pompa de Ron, la formas resultantes son tan puras y tan simples que llegamos a considerarlas como una abstracción matemática. Sorry for Tony, but I hope you have an idea. Well, in the 60s, Frei Otto, a well-known German architect, started making structure, big structure, using soap film. And the Department of Architecture of the Stuttgart University was built using a model with on the right, on the left, to construct the department. And this was a model made by Schwarz, the first to obtain a solution of this kind of minimal surfaces. And this was used by the famous tent of the Munich Stadium, made by Frei Otto. Of course, the minimal surfaces are a model, but there is no gravity. This is tons of kilos, etc. So you have the idea of how to make a structure, then you have to make something that is still there for 100 years and that. It's just an idea of the minimal surfaces, but then built using the model is quite another problem. There is also advertising. This is the first poster that was made in the history of art. It was made in exactly the model of Manet that Millet, he said, he made a copy of the one of Manet, almost a copy. And Mr. Pierce, who made this famous transparent soap, had the idea of put a little soap here. That was not in the original, of course. He bought the painting. The painting is still in the office of the director of the Pierce. It's not his Unilever, but it is the same. And then they start making poster to sell the soap. Now they use computer graphics to make the advertising. And you have many. It's interesting that in nature you find also periodic minimal surfaces of different type. This was studied by Pierce, but not the same Pierce, another Pierce, of the NASA to build a structure in space, in outer space. And that thing happened in 1985 in mathematics. Kofta, Hoffman, and Meeks solved the problem of finding minimal surfaces with topological order more than 0, at least 1. That is a hole in the structure. And they use the image of the equation of the surface that Costa said perhaps in the solution to see the structure on the screen, and using this, they was able to divide it in pieces, the surface, and they proved that this was the solution of the problem. So that is the first really use of a computer graphics to solve a real problem in mathematics. And then they discovered that there was topological order. It also was one of the first examples to make a 3D model, 1990. And also software that is a proton bracket that is absolutely free. You can make animation with software. The software is there and you can use it. And you can also produce bubbles that are impossible in the real world. It's like this two bubble is impossible. Something like that, there is no hole in the bubbles. And John Sullivan, made also a better solution to the problem of Kelvin. What's the problem of Kelvin? Was to have a structure, polyhedral, fixed volume, that fill the whole space. He proposed a solution, and in 1994, Werner Phelan at Dublin, the University of Dublin, find a little better solution, and this is the DEA solution. And this was a model for the Olympic swimming pool, Olympic Games in Beijing, by a group of Australian, Chinese, and German architects. And this is the model of the structure. This was a sort of basin full of salt water. The structure respects all the angles of plateau, and there are also bubbles all around. And during the evening, much better. You see that the angles are exactly the same, while the fish, of course, is rendering, not the real one. This is the interior. You see they use the solution of the problem of Kelvin. And the exhibition, we were able to have the only maquette that exists of the project, and this one. So this was the exhibition. Now, I just changed the PowerPoint because it was possible to put all together there. And just 1 minute. This one. Fire made from division. Okay. So now we are at the Biennale of Venice about 15 years ago. There was this very large structure. You see the person there. This is an exhibition in Milan. Bubbles, connection of bubbles everywhere. And also the solution of Kelvin by Werner Phelan. And all the things together, also with other things, but I'm particularly interested in the structure. For example, they made this on top, or he made this on top of the Metropolitan Museum. He built all the structure with glasses and windows, so it was possible to see all the town walking on the ceiling of the Metropolitan Museum. We have an example here. All connection with the structure, minimal surface, etc., etc. This is another example, enormous bubble where you can jump in. His name is Thomas Saraceno, who is originally Argentinian. He is now one of the most famous architect, engineer. He worked in the NASA. He has a laboratory in Japan, etc. But we discovered about 8 years ago, an exhibition in Torino, we were together, that he is my cousin. Because the brother of my father went to in Argentina with the family of Saraceno, and one of the cousins of him married a cousin of mine. So the world is really small. So one of the inspiration, of course, was Buckminster Fuller was inspired by the drawings of radiolaria. And this is another incredible structure of real radiolaria. There was also the book of Haeckel, but nobody said that it's impossible to see something like that. Darcy Thompson, exactly. And these are the real drawings of the Haeckel. And this is as I showed you before, Sullivan, the solution of this problem. But the problem, this was computer rendering. A few years ago, it was possible to build with real soap film the solution of the problem. This one of the picture, and this is the solution. And this became very, very famous, this picture, because it's only made with soap film. And was made by the group of people in Dublin. And the team leader was Ruggero Gabrielli, who was at the University of Trento, but they refused to give him any money to make this research. So he went to Dublin, and so his experimental realization of the Wera-Fella structure in dispersed liquid foam. The interesting thing is that the paper was published in Philosophical Magazine Letter, was exactly the same magazine where Colt Kelvin posed the question more than 100 years ago. So the Physical Magazine Letter asked them, please send to us the paper. We want to publish the paper in the same magazine. Well, a little about mathematics. So I told you that the problem of Plateau and see that you have a contour and you put it in the water, then you obtain a solution. So the boundary problem was studied by many mathematicians. The first one to study the Plateau problem was Timor Rado. And here are the two original papers, the problem of Listari and the problem of Plateau, and on the problem of Plateau in the 1930s. It was three-dimensional problem, considered in 3 dimensions. Jesse Douglas was the first field medal studying, was also in absolute one of the first field medals. The solution of the Plateau problem, the most general form of the Plateau problem, the American Mathematical Journal. And because it was also, in a few years, it was interesting that it was, in a sense, easier to study the problem in any dimension instead of the 3 dimension, the physical space. And of course, Ennio De Giorgi. Ennio De Giorgi was only a big problem. He was not interested in writing anything. So his paper was known to all the people working not only in minimal surfaces, but the paper was written only in the 70s, after 25 years. So these are, of course, in Italian. They refused to write in English. So these are the two most important, not most important, two of the important papers of Ennio De Giorgi. In particular, there is a question related with Nash, who received the field medals in economy. And this is the actor who was John Nash in the film, Beautiful Mind, Russell Crowe, because there is a problem that they prove one of the problems posed by Hilbert at the beginning of the 20th century in two different ways, and one had no idea that the other was working the same problem. The first was Ennio De Giorgi, and Nash 3 months later. Few months later, Nash had his illness that made it impossible for him to work for 20 years. And he received the Field Medals of Economy for the work he made many years before. It's not, of course, it's impossible to say that this was just the case of his depression, etc., but there is this coincidence. And this is the paper that was published in the 60s and the 70s. Because the technique used by De Giorgi, called the perimeter theory technique, was known to all of us who were working in minimal surfaces, but was written only finally in 1972. And this is a very important paper made together by Ennio De Giorgi and Enrico Bombieri, Enrico Giusti, in 1969. Giorgi was more than 50. And Bombieri received the Field Medals, working also on minimal surfaces. And he was in the University of Pisa, then the Institute of Advanced Study in Princeton, at the beginning of the 70s, when he received the Field Medals, asked him to come to the Institute, and he's still there. In 1974, received the Field Medals. And then, this is another young Italian mathematician who received the Field Medals in 2018, working also on minimal surfaces. And all the newspaper in Italy and all the world has a picture with him with a great big soap bubbles. Not only this, but Karen Nulenbeck received the Abel Prize in 2019. And there were 2 pages on the New York Times and the Mathematical Universe in a Bubble, dedicated to her and story, etc., etc. This was presented to the little Brazilian film. There is only a bubble goes around in an empty building. And this is my book on soap film. And I received this was made for the Biennale of Art in Venice. 2 structures that you obtain inside the cube, and it was observed by Plateau, of course, at this Biennale. And also I made 2 days, special 2 days in Venice on bubbles. And then Perugia. This is the marvelous Renaissance building palace called the Palazzo dei Priori. And the exhibition on soap film, soap bubbles, was inside there. There were 60 paintings coming all over the world, from the 15th to contemporary artists. This is the painting that you saw before in Newton looking to the boy. This is myself with the director of the museum. And I will just give you an impression, because at the end, you will see 2 minutes of the movie made inside with nobody, so you will have a clear idea of the exhibition. And so you see, and this is Bruegel, that's in front of you. There are also the original book of Newton, of Darcy Thompson, etc., etc. This is Dujardin. There was a poster of the exhibition. And this is also the contemporary Beckman. And you will see also Man Ray, this one. And there was, I think it was also the original poster made by the painting of Millet. And also a little book for children. This is sort of panoramic of the edition. This is the poster. This was open until the June of the 2019. And then I will conclude saying a few words on a topic is related to this, but also I would like to a little bit spend a few words on just the days we are living. During the COVID, in fact, was the end of my conference in Venice. It started in 1998. Because for 2 years it was impossible to organize a conference in Venice. And then I realized that after 22 years, it was better to close the conference. But during the conference, we made two things. One was made by the Springer. Springer asked to all the director of series of books to write something in what they were doing during the time of coronavirus. And the Mathematics of Light first collection. And with this is what I write. I wrote, Some Bubbles, Vanitas, Venice. Because I was, of course, alone, close in my room in Rome. It was impossible to go to Venice, of course. It was impossible to move. You know, all of you know very well the problem. So I made a paper saying what I was doing. This is the Accademia Istituto Veneto di Scienze Lettere e Arti, Palazzo Franchetti on Canal Grande. I am very pleased to be member of this place. It's a really incredible place, where there was the last conference of the last 6-year-old took the birth. This is Venice. This is Venice. You notice something strange? Of course, there is nobody. And the water is still. You will never see again the water like this in Venice. Because there are boats, there are people. There was no wind this day. There was no boat. And this is Piazza San Marco only with the police. So this is why I write this paper on Some Bubbles, Vanitas, and Venice. Because we had no idea what was the future. And then there was a Magic Math 8, Dreaming Venice, because it was made in 2022 without the conference in Venice. So it's a very large book of more than 600 pages. And I pretend from Springer that the cost must not exceed 40 euros. And I said there another version of the same paper called Dreaming Venice. And before the publication, we insert this page, because the book appeared just 1 month later. And I will end saying something on the time of war. This is Leonardo, a journal of MIT Press. I'm a member, it's 25 years that I'm a member of the board of Leonardo. And 22 years ago, I wrote, I even don't remember which was the war. I wrote a paper, Only Bombs Are Intelligent. Perhaps it was a war in Iraq, I think, because you remember there was the intelligent bombs. Make selection. And I received, the journal received many papers by scientists, by artists, etc., etc. Then I made a sort of answer to the people who start sending paper on this next year. Then another one, because there were wars all the time. Can ideas and words be useful? Is Vanitas to say something about that? And then in 2005, a renewed call for papers. And then in 2018, are we an intelligent race? These were written because my son, his wife, and my two granddaughters were in the same building where downstairs they killed 21 persons in Paris. So I written this, where there is written that 3 pages I wrote in one night, I think. And usually the editorial on Journal of Mighty must be half a page. I said, well, or you publish entirely my paper, or you will not have a single word, because there is something that I try to explain why. And so now they asked me to make another call for papers. And my idea, I have not written yet a paper, is to use this without some words, just for the young people to understand what it is, when, why was made. And this is not a painting by Pablo Picasso, it is the copy of the painting of the same dimension, size, made in Guernica in ceramics, at the entrance of the town. So I don't know if you know, Guernica was the first town used as an experiment to be completely destroyed. There was nothing to destroy. It was the civil war against Spanish in Spain. There was absolutely no, anything related with war in Guernica. It was just, and it was the first time that a little town was completely destroyed using the airplane. And this is the reason why, of course, Picasso refused that the painting go to Spain until the death of Franco. Now is the Marina Sofia. And I would like to end this because I've always been interested in art and then in mathematics and in cinema. And the reason is very clear. And you see why. This is my father on the left. With Picasso in 1953, they made together a movie of 50 minutes in Valoris. And this movie is very beautiful, I must say, but it's also exceptional. And every time there is an exhibition in the world, they ask me the permission to use the part of the movie, because in the film there is Picasso, who made a fresco long 25 meters all the night. In the film there were 5 minutes. And then the morning they end, Picasso and my father, they went to sleep. And they come back in the afternoon. Unfortunately, Picasso has told some workers that they need to have this wall all white for the morning. So the workers saw the painting of Picasso, but they said, well, the master asked us to make the wall all white. And so they painted in white all the wall. So the only place where there is this fresco is the film of my father. So now there is the last slide, but then there are the 2 middle movies, just 3 minutes in total. So this is the end of the slide, but then we have to project. So I close my presentation. And yes, Javier will show you the first one on the exhibition, and the second one a few frames from my movie on something. I think I have closed my.
Sí estamos viendo, pero no se reproducía el video.
Now let's have a look at some minimum energy models, that is, providing maximum stability for given shapes. This is what we obtain by immersing a cubic form in the soap film. And this is what we get with a tetrahedral form, with a bubble at the center of the structure. The color depends on the thickness of the film and the type of soap used, as Boyce observed at the beginning of the century in a classic work on soap bubbles. If we use a dodecahedral form, we get an incredible number of soap films inside the structure, which create extraordinary light effects.
Thank you.
Thank you very much, Michele, for this beautiful talk and all with its beautiful content. It's been so nice and inspiring to listen to you. There are some questions here in the chat. There is this question which maybe it was at least partially answered during the talk, because it was maybe during half of the talk. And they ask whether there are currently painters with the same quality of detail and interpretation, like more, I understand modern artists, because you were talking about all this connection and like ancient or like Middle Age painters and some.
There was one of the painting in the front of the maquette of the Olympic swimming stadium was Marco Paolini, who is one of the most famous Italian contemporary artists. And there are several also. There is now, and I don't remember the name. It was complicated to have it. The Japanese who used to make a sort of experiment with the soap film, soap bubbles, to produce a work of art. And there are several other people who make. The problem, of course, with making this kind of, there was an incredible, beautiful, enormous machine to produce soap bubbles in Piazza San Marco in Venice about 10 years ago. But it was impossible to locate where this enormous machine was. And there was also another Biennale in Venice. There was she's an artist who lives in Zurich. To remember now the name. It was, the part of the Biennale was inside the port. Is always inside the port of Venice, the old port of Venice. So there is a lot of angles and walls, etc. This machine was put in an angle that you walking, you don't see the machine. At a certain moment, it was pushing some bubbles towards you. So all the people were frightened because they realized what was happening. And then they saw the simple soap bubbles coming. It was one of the most beautiful, attractive event of the Biennale of Venice of this year. So I'm not sure, I cannot be sure, but they are not painters of the soap bubbles and soap film anymore. Soap bubbles, in the sense, is an old-fashioned thing in painting. So, but probably there are. It's possible to have an idea, a complete idea of the situation in modern art. So I cannot say no or yes. Probably yes. I have, for example, I have no idea. I have absolutely no information about South America. Absolutely nothing. Or in Asia, except Japan, so Africa. I have no idea. So because I only at the Bibliothèque Nationale de Paris, I think there are more than 1,500 engravings in work of art on some bubbles. So the problem is to select them. But I can say there was really an European interest, the north part of Europe, and so also in Italy, but the north part of Italy, from the 16th to the 18th century. Mm-hmm. And there was the diffusion. There is example in Japan, etc. It was probably the diffusion of this idea, but I really don't know. And I don't think that there is nobody who has studied the story of the diffusion of soap film. It's a really vanitas thing to destroy when you are looking for it. So, but I don't have a definite answer.
Yeah, in a more general way, like you've been studying mathematics and art like since many years ago. And I wonder whether you see a difference, or like you see the when the computers got involved in this relationship between mathematics and art. What's, in your opinion, was it like a big revolution, or it's just one more tool?
Well, I took part in the first Biennale of Venice, where there was the use of computer. I think it was 1984. The same where there was the film of Bubbles. There was, I don't know why, inside the section of technology, because there was no technology at all. It's very natural. And there was a big discussion that took place for 2 years. If an artist has to know the language of the computer, that may, at the time was the basic Fortran, etc., or if he have his creativity, he have no idea of how to use a computer, and he try to do something. Of course, it was an idiot question, because you cannot use a computer. It's the same that writing a book without using the pen. Probably you can do, of course, not considering the computer. After 2 years, all the people, there was a big discussion on the newspaper, etc., etc. And at a certain point, they realized that if you don't know how to use a computer, it's impossible to use it. It's not like a ball that you could play the ball if you do what you want. It's out of question. So you depend on software. This is one of the main reasons why there are two kinds of architecture. Popular architecture are made using CAD that is used everywhere in the world. Use the law of perspective, Euclidean geometry, etc., 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 and the houses are equal all over the world. The same CAD, the same houses. The big and famous architects or artists, they produce their own software to produce, for example, the incredible thing that David was able to do. It was impossible to make with the usual software, etc., etc. So the difference is to be really interesting from the point of view of architecture and art. You must be a clever expert in software, because otherwise, and of course, as we are producing millions and millions of images, we film everything. My impression is nothing will be left, also because it's completely wrong that if you make something digital, it will remain forever. No, absolutely not. Until a new generation of computer. So, it's true. The thing that Thomas Saraceno was able to do is mention incredible. He's able to do something that was unthinkable. Absolutely, and there are many, many others. So it's always, the problem is not really the idea. You must be a creator. This is the problem. And this is not difficult to determine who will be a creator, who will never be a creator. Then, of course, a new beings, computer, etc., is a marvelous tool.
Well, thank you very much. There are some congratulations and thanks from people in the
I am able to say muchas gracias. Hasta luego. Be in touch.
Y bueno, pues muchas gracias a todos por acompañarnos. Esta fue nuestra última sesión del semestre. Esperamos verlos el próximo semestre con un nuevo ciclo que empezará a partir de febrero, marzo del próximo año. Estén al pendientes. Muchísimas gracias. Hasta luego.
Ciao, Tony.
Bye.